Today we're going to be talking about radicals. Now before we get into radicals and what radicals are, I just want to show you something very simple, which will be a core concept in radicals, or square roots as many call them. Here we have a problem, 5 plus 1. We know 5 plus 1 is 6, right? And we know 2 times 2 is 4. Simple multiplication, simple addition. Now, if you ever had to check, well, does this hold true, what would you do? You would simply undo the problem. And by that I mean you take 6 and you subtract what you're adding, which in this case is 1, and you see if number 5 comes back. And of course it does, because the number before 6 is 5. And here for multiplication, if you want to check to see if this is true, you'd say, hey, what's 4 divided by 2? And we know 4 divided by 2 will give us 2. So these are very simple concepts, but it's just important to have an understanding of these, because you're going to need them when it comes to radicals. So I'll erase this and we'll jump right into radicals. Now this isn't a radical, but it's obviously going to be an important concept. If you see this, which is 3 raised to the second power, or known as 3 squared, you would say, hey, well, I know what this is. I'll just write it out. It's 3 times 3. And 3 times 3 is obviously 9. And if this power over here was 3 or 4, you would say, you just write it out as many times. There's only 2 here, so you just write this out 2 times. Now, like we went over in the first example, where multiplication can be undone by division and addition can be undone by subtraction, you can undo a number being squared by taking its square root, or its radical. So we could say 9, the square root of 9 is equal to 3. That undoes this. 9 is the same thing as 3 squared. The radical undoes the square, this little exponent here, and we get 3. Now, you should refresh on your multiplication times tables. I'll probably put them up here right after. Actually, I will, just so you can brush up, because these are rational numbers here. 3, 4, 5. When you multiply them by each other, they make these numbers called perfect squares. Perfect squares are very easy to take the square root of. It's just a number what number times itself gives you this number. 3 times 3 is 9, 2 times 2 is 4, 4 times 4 is 16. So I'll put up a couple examples just for you to remember, and we'll do some more problems. So here we have a table with what I was talking about last time, perfect squares. They're all just numbers times each other. I just listed 1 through 9, but you should know a good amount of them after 9 up to at least 12. But right here we have a problem. This says what's the square root of 36? Now it's right here, but if you didn't know, you could ask yourself, what times itself gives you 36? Well, we know that, and that's 6. 6 times, if you want to check it, you would say, well, 6 squared is equal to what? Well, 6 squared is the same thing as 6 times 6, and that is 36. Same thing applies here. Oops, sorry about that. Same thing applies here. 100, what's the square root of 100? Well, what times itself equals 100? It's not here, but, you should know. 10 times 10 equals 100. And obviously 10 times 10 is the same thing as writing 10 squared. Now we have an interesting one over here. What is the square root of negative 16? Well, a lot of people might look at this and say, well, 4 times 4 is equal to 16, so this must be 4. And that's not true, because 4 times 4 is 16. 4 and 4 are positive numbers. So you're like, oh, maybe it's negative 4. Well, negative 4 squared is equal to 16 as well. A negative times a negative is a positive, and a positive times positive is a positive. So you might be like, well, what the heck is this? There's a negative inside here. What can you multiply together and get a negative? A negative and a positive. Oh, okay. 4 times negative 4. Right? That equals negative 16, right? It does, but these aren't the same number. 4 does not equal negative 4. So these can't be solutions. So let me clear this up and we'll go a little bit more in depth into this problem. So here we have the problem, square root of negative 16. Now, like I said before, this isn't a perfect square because nothing times itself equals negative 16. So how do you solve for this problem? Well, like I said before, you could only really take the square root of a positive number because when you multiply negative numbers together, they become positive, and when you multiply positive numbers together, they become positive. So if you have a negative number inside the square root, this is what we like to call an imaginary number. It's not real because, like I said before, there's nothing you can multiply by itself that will get you this number. So the way I like to solve these problems is I say, alright, let's pretend this is in here. Let's make this simple. This is in here. This is the square root of 16. That's a lot easier to solve because you know the solution there is 4. That's the square root of 16. But that's not the square root of this. So to denote that this is an imaginary number, we just write I. And 4i shows that this is a solution and it's an imaginary number. So that should cover it really, for now, this lesson at least. So you need to know your multiplication tables, what numbers times each other will give you what numbers, and the square root of those will give you back that answer, and that will be your solution. If there's a negative in there, just solve for it without the negative and use the I to denote it's imaginary. So next time we're going to deal with non-perfect squares, because you can take the square root of non-perfect squares. They won't be rational numbers, they'll probably be irrational, but you could still solve them and get approximations and all that good stuff. So tune in next time.